this, all right? And I'm going to use oxygen as an example. And so here we can see the oxygen term symbols, right, that I asked you all to do in the last exam. The triplet sigma ground state, the singlet delta first excited state, the A state, and then the B state, the second excited state, the singlet sigma G plus, okay? And all of those, luckily for us, transitions from the ground state to any of these states are forbidden because of the different multiplicity, right? We can't go from a triplet to a singlet or a singlet to a triplet, okay? And so what I've done here on this potential energy scale, I've converted these into wavelengths. And so you can see in this region, this AA, that stands for atmospheric bands. And we're lucky that those atmospheric bands are forbidden, so we don't observe those atmospheric bands, because in this region right here, this corresponds to visible light, right? So this from 0 to 193 kilojoule per mole, you can see that that's right around 620 nanometers. So excitation from this X state to this A state, or from this X state to this B state, would actually remove visible light from our atmosphere. Think about that. There's 20% oxygen in our atmosphere. And these lines would correspond to visible light transitions. So we would actually have like a very different looking sky and very different light available to us if oxygen could absorb those bands, okay? Luckily, it does not. And so what's observed instead are what's called the Herzberg Continuum and the Schumann-Rung system, okay? So that corresponds from this X triplet state to this A triplet state for the Herzberg. And then for the Schumann-Rung, it corresponds from this X triplet state to this B triplet state, okay? And what I want to point out here in the case of oxygen, the overlap is terrible. Right? You notice that? If I were to go from a vertical transition, let's change colors here. So if I were to do vertical transition for this Herzberg continuum, for example, right? The vertical transition going straight up, you can see there's not very good overlap at all, okay? However, if we looked at the Schumann-Rung, the overlap actually gets pretty decent. Look, it's going right at the potential energy scale, okay? Corresponding to about 200 or so nanometers. And as we go further and further up, the overlap gets better and better and better. And what I want to point out as far as atmospheric chemistry is concerned, it's this band right here that's responsible for ozone layer production, okay? We have an ozone layer because molecular oxygen will absorb these UV wavelengths. And as you can see, that's creating photofragments. And those photofragments, most notably the O triplet state, will go on to react with O2 to make O3, right? And you can see also even in this Herzberg continuum, right? When we get about to 250 or so nanometers, that's about 250 nanometers where ozone production starts. You can see we're photofragmenting an oxygen molecule to make those O triplets, which will go on to make ozone. So that's also why we call this region of the electromagnetic spectrum the vacuum ultraviolet region, because if you shine light of these wavelengths, about 250 nanometers and below, if you shine light at atmosphere, you will start creating ozone. And so the vast majority of that light will get absorbed by oxygen and go on to create this toxic gas, ozone. So typically, if you want to use these wavelengths of light in an experiment, you do it under vacuum, where oxygen is not going to be absorbing those wavelengths, okay? So all the same, I'm using this to talk about atmospheric chemistry, but you can see very much the UV-Vis spectrum of something like oxygen is super important to atmospheric chemistry. Okay, so let's continue along and let's actually look at the spectrum of O2. And here you can see I'm focusing in on the high energy region, the VUV spectrum, the vacuum ultraviolet region. And there's several things going on here. So for one, you can see I've shown the vertical transition from the X triplet state to the B triplet state. And you can see at the minimum, right where I just draw this line to that bottom level, we know that bottom level has a wave function, up here. And there's a very, very, very small but finite probability of finding it stretched way out to there. And if you look at its absorption spectra, so keep in mind that's about 206 wave numbers or so. Here's about 204 wave numbers or so, pretty close. And you notice this absorption cross section is crazy small at that 200 wave number region. Okay, so here this is a log scale, and we can definitely have absorption spectra where we plot, instead of A versus wavelength, we just plot sigma versus wavelength. Perfectly fine to have an absorption spectra like that, and it's actually incredibly useful to plot an absorption spectrum like this because we don't have to specify concentration or path length, right? This is just literally like how much light a given set of oxygen molecules are going to absorb, okay? And then, of course, when we factor in the path length and the concentration, we can convert this cross-section into an actual absorbance. And the important thing, what I want to note, is in this vicinity of 200 nanometers, you can see the absorption cross-section is quite small, 10 to the power 23. So because this is a log scale, what that means right there is 10 to the negative 23. Really, really small. But as you can see, as we get to higher energies, which on this scale, means I'm going up and up and up and up and up and up, and I'm getting closer to the potential energy surface, which means I'm having better overlap. That means I'm getting more absorption, right? Look, the absorption increases by like a factor of 1,000,000 over the scale, right? From 10 to the negative 24 to 10 to the negative 18. That's a power of 1,000,000 fold in the absorption spectra. So for example, if we had a path length and concentration at, I'm just going to say at 179 nanometer, okay? Suppose we had an absorbance of 1 based on our concentration and path length, okay, at 179 nanometer. That means our absorption at 204 nanometer would be 10 to the minus 6 absorbance units, all right? So we can really see in the absorption spectra this notion of this vertical transition and overlap with the underlying wave functions. Okay. What I also want to point out on this absorption spectra, we can see several features corresponding to different vibrational levels. And so we've got, a vibrational level here and here and here. And I'll note all of those, right? We see all these different families of peaks, and each one of those families of peaks corresponds to each one of those vibrational levels. But you can also see within each one of those families, there's several more lines, and those correspond to the rotational states. So we observe this in this oxygen spectrum because, for one, it's a gas. Our gases rotate. If this were liquid oxygen or solid oxygen, we wouldn't see those rotational levels, okay? But also, we see various vibrational features as well. So if we have a gas and we have a powerful enough spectrometer, something with crazy resolution, when we do the UV spectra, we are able to probe the electronic transitions, the vibrational transitions, and the rotational transitions all at once because our UV light has enough energy to excite all of those levels, okay? And of course, what we're seeing on these new levels, we're seeing new change by plus or minus 1, we're also, I'll put a delta there, we're also seeing J change by plus or minus 1 because those are the allowed rules, right? And that's why we have so many of these lines in this UV-Vis spectrum. Now, what you're used to seeing is just, big peaks like this. And that's because typically, if you've done UV-Vis on a liquid or a solid, you're not going to be able to resolve the rotational levels. But also, if you've ever seen a UV-Vis spectrum that has some features, so maybe it doesn't have this nice, beautiful Gaussian, but it has like different features like that, right? All of those different features correspond to the different vibrational levels. And I'll show you a few pictures, okay, a few examples.